So again, this is our second quadrant angle. We found 5 pi over 6 based upon the original value for theta that we see in the problem. And yes, the R value is 4 based upon what we see in front of this quantity. Let me drop down the altitude to make some further connections. And as you see, I'm drawing the adjacent side, -2 root 3, the opposite side 2. We can highlight theta prime, and we can calculate theta prime as pi minus 5 pi over 6, which is just pi over 6. Keeping in mind that we can really only do right triangle trig with 2 acute angles and a 90-degree angle. Before I continue, let me ask you to reflect upon the previous page example where I had drawn for you the second quadrant angle with A and B, theta prime, theta. If you think about this depiction here, we actually did in fact know that R is the hypotenuse, and given this particular equation, well, the cosine of theta is easily known to be A over R, and the sine of theta B over R. And again, looking at your picture, you can see, and even though this is theta prime, it is in fact a second quadrant angle, so we can say that the cosine of theta equals adjacent over hypotenuse, A over R, and the sine of theta is equal to B opposite over R hypotenuse. So we are going to use right triangle trig throughout this lesson. Let's continue. So multiplication and division of complex numbers. The product and quotient of two complex numbers. Let z sub 1 equal r sub 1 times the quantity cosine theta sub 1 plus I sine theta sub 1, and z sub 2 equal to r sub 2 times cosine theta sub 2 plus I sine theta sub 2 be complex numbers. So the product of two complex numbers, z sub 1 and z sub 2, in other words, this quantity, as I indicated up above, times this quantity, again from up above, factoring out an r sub 1 and r sub 2 in the next step, leads to this expression. And more importantly, the derivation leads to this formula. This right here, r sub 1 times r sub 2 times the quantity cosine theta sub 1 plus theta sub 2 plus I sine theta sub 1 plus theta sub 2 is what we're going to focus on when finding the product of z sub 1 times z sub 2. So this is just a derivation to help you get there. Focusing on this is what our real objective will be in a little bit here. The quotient property works like this. Z sub 1 over z sub 2 equals r sub 1 over r sub 2 times the quantity cosine theta sub 1 minus theta sub 2 plus I sine theta sub 1 minus theta sub 2. Let's highlight this formula. And let's note the difference between the two. With the product property, we're utilizing addition for our theta values, and for the quotient property, subtraction. Let's also note that z sub 2 cannot be equal to 0, because as we all recall, we can't divide by 0. So we have to make that a little note. Moving on to example 4. Okay, so if z sub 1 is equal to 8 cosine 120 plus I sine 120, and z sub 2 is equal to 6 cosine 150 plus I sine 150, then find the following. So the product of z sub 1 and z sub 2, again utilizing the product property, we'll go up and pull that up for you here. So r sub 1 is 8, r sub 2 is 6, so 8 times 6 times the quantity, the cosine of theta sub 1 plus theta sub 2 plus I times the sine of theta sub 1 plus theta sub 2. If we go ahead and start simplifying, we get 8 times 6, 48. Cosine of 120 plus 150, well, let's first add these two angles, so 270 degrees. 270 degrees. And simply enough, we know that the cosine of 270 from the unit circle is just 0. We know that the sine of 270 from the unit circle is -1. Simplifying one more step by distributing the 48 leads to 0, and then -48i, or just -48i. But again, you can see that we do in fact have standard form with 0 as our a value, -48 as our b. So a plus bi form, and -48i is acceptable in this instance. We can also make a quick connection to the ordered pair on the complex plane as 0, -48. Let's move on to part B. So z sub 1 divided by z sub 2. So again, if we go back to the previous page and see what that particular formula is all about, we divide our r sub 1 and r sub 2 values and multiply times cosine theta sub 1 minus theta sub 2 plus I sine theta sub 1 minus theta sub 2. So let's do that simply by, again, dividing 8 over 6, our r1 and r2 values, and then we'll take the cosine of 120 minus 150 now, plus I sine 120 minus 150. We'll do the math on this right away, with 120 minus 150 being -30, -30. And although that's a negative angle, it is a unit circle angle that we can calculate. So 4/3, of course, as we simplify 8/6. The cosine of positive 30 degrees is radical 3 over 2, but so is the cosine of -30. It's a fourth quadrant angle. Cosine of 30, of course, is positive as well in the first quadrant, plus I times the sine of -30. So the sine of positive 30 is a half, but this is in the fourth quadrant, so -1/2. A little bit more simplification on our part. 4/3 distributed to radical 3 over 2, or just 4 divided by 2, which is simply 2. 2√3 all over 3. Distribute the 4/3, and we get -2 over 3. Don't forget your I. And this is our final answer. And this is A, 2√3 over 3. This is B, -2/3. And again, if we were to make a connection to the ordered pair, maybe on the complex plane, this would be your A value, and this would be your B value. So it would actually be an ordered pair in the fourth quadrant. This is positive, this is negative, A comma B. So it's a fourth quadrant angle. All right, moving on to powers of complex numbers. To raise a complex number to a power, apply repeated use of the multiplication rule. The multiplication rule can be generalized to any finite number of factors. Thus, we'll start off with what z is simply equal to. So z equals r times the quantity cosine theta plus I sine theta. So if we square the quantity, not just on the left but on the right as well, we end up with r squared. And something interesting happens in utilizing that product property that we just observed. The cosine of 2 theta is what we're going to have, plus I sine 2 theta. In other words, you're adding thetas, so you end up with 2 theta. Moving up a degree, z cubed is equal to r cubed times the quantity cosine 3 theta plus I sine 3 theta. And the pattern continues until you see, in the next instance, furthermore, r sub 1 times cosine theta sub 1 plus I sine theta sub 1 times r sub 2 cosine theta sub 2 plus I sine theta sub 2, which leads to this expression, an n number of complex numbers essentially multiplied, factoring out r1, r2 all the way to rn, leads to this quantity, And we move forward to the next page. If in the above formula all the moduli were the same and all the arguments were the same, we get de Moivre's theorem. Here's what de Moivre's theorem suggests. If you take any complex number raised to any exponent n, it is going to be equal to r times the quantity cosine theta plus I sine theta to the n power, which is also equal to, in simplifying, r to the n power times the quantity cosine n theta plus I sine n theta. This part of de Moivre's theorem is what I want to highlight. And we're going to use that in our next example. So example 5. Evaluate negative 2 root 3 minus 2i all to the 5th power. Okay, so we are going to use de Moivre's theorem here. To get the ball rolling, I want you guys to maybe note that the ordered pair a comma b, negative 2 root 3 comma negative 2, I'll go ahead and highlight that there, is something that, again, we need to go back and make connections to, even graphically speaking. Let's also identify our n value. In other words, what are we raising this complex number to? It's raised to the 5th, so n is equal to 5. All right, let's get the theorem going here. So r. Now, r doesn't pop out at you here, so we're going to have to calculate it. So r is going to be equal to a squared, so negative 2 root 3 squared, plus b squared, so negative 2 quantity squared. Notice I put parentheses around both. If we simplify, let's go ahead and do this. So I'll do the square root, and I'm going to put parentheses around my negative 2 square root 3, square it, and then add, we know this is 4, but let's type it in. And we end up with an r value of 4. And again, remember what r is representing. R is representing the hypotenuse of the right triangle, of which, well, if we look at the ordered pair negative 2 root 3 comma negative 2, this is in the 3rd quadrant. Okay, so understanding again what this right triangle looks like in terms of not just the respective sides, opposite, adjacent, but also, of course, the appropriate quadrant. Okay, so let's go ahead and calculate theta as well here. Remember, theta can be calculated by taking the inverse tangent of opposite over adjacent, or in this case, b divided by a. Okay, the math on this is simpler than you think, or may think. These cancel. Okay, so you basically have 1 over root 3. So the inverse tangent of 1 over root 3, or if we all recall, you can simplify that as root 3 over 3. And since this isn't a very obvious trig ratio, I'm going to go ahead and convert my calculator to degrees and just type this in. Make my life easy here. So if I go ahead and convert to degrees and take the inverse tangent of root 3 over 3, we end up with 30 degrees. Okay, now remember, 30 degrees is really not the angle we want. I say remember what quadrant we're supposed to be in. I still want you guys to note 30 degrees. Okay, we can also, in this instance, knowing that it's not technically in the 1st quadrant, but it's in the 3rd quadrant, let's put a little theta prime here. So we're really looking at a reference angle. And then let's start graphing. When we start our graph, we need to consider, of course,